Now mold filling is little more rare, and it is little more difficult both in terms of computation as well as interpretation and usage, because it takes a lot of computation time. So because it is more difficult, little more rare, we will spend little less time on this module, but I'll still go through some of the key points in this lesson. First of all, we'll ask the question, do we need to do mold filling simulation? Because it's inherently difficult and complex, and you don't get very accurate results. So we'll ask, is it important to do it? In which cases it is definitely we should do mold filling simulation. Then a little bit of how they model mold filling, the governing equations, and finally we'll go into mold filling plus solidification simulation plus stress simulation, and what are the complications and how people can handle it little more comfortably. Okay. So let's start off. So the two purposes of mold filling simulation is, one is to predict gating or filling related defects, and number two, if you have done a gating design, you want to find out, is it going to be effective or should I change the gating design? So you need to do these two things. So by and large, if you say why you definitely need to filling is, remember we said that one of the first rules of good gating design of fillability, we said it has to have complete filling. And if you remember, we also said one of the things we should check is the filling time versus solidification time. If both are almost equal, then that means solidification is happening as a mold is filling, and then you can have cold shuts and misruns and other filling problems. So when these two are, when are these two likely to be equivalent? When heat transfer from the mold is high. When is that going to happen? When you have thin wall castings and in a metal mold. So metal mold plus thin wall casting combination is when you have to definitely worry about filling simulation plus solidification simulation. Otherwise you cannot predict many of the related defects. Okay. Now there are various methods of tracking the flow. So what you need to do in flow filling is, you need to track where the fluid front is. Like in solidification we are tracking where the solidification front is. Here we want to look at where the flow front is. Okay. And there are various methods for doing that, which are suitable for different kinds of materials and shapes. Okay. So we'll look at essentially 2 or 3 methods called as marker and cell method, which is MAC, VOF, volume of fluid methods, and a new method, relatively new method called as LSM method, level set method. So in a marker and cell method, what they do is they have fixed cells, and they say this cell is empty or this cell is filled. Okay, that's a simple way of doing that. And in a sense, and you can put particles in those markers in those cells. That's a simple arrangement of description of how this works. The problem is that because a cell is either filled or not filled, you really don't know what happens to partially filled cells. So this is okay as a starting point, efficient computation, but in reality it's a gross approximation of what happens in a real mode. Okay? And if you've seen the slow motion video of the flow filling yesterday, I hope you enjoyed that. You never realize what all happens even in a water flow in a mold. Okay? And I hope you enjoyed that last, if venting is closed, what happens to that? It doesn't fill at all. So the next big improvement in this was volume of fluid. Okay. So what they do is, each cell they can compute saying it is so much percentage full on a scale of 0 to 1. So 50% full means, or 25% full or 70% full. It only knows the value. But once you know the value of a cell and the values of the neighboring cells, you can in some way draw the boundary. So it is still cells, but now cells have not 0, 1, but between 0 and 1 values also are given, are computed. So you can now start tracking the flow front a little more accurately. That is little improvement on this. But even better than that is a level set method, which is relatively newer technique, and people have still not used this in computation programs ever commercially now, because any computation is a huge effort, especially in flow mold filling. But this can give you even more accurate curvatures, and it's also easy to link this method with both flow and solidification much more nicely. So this LSM is the latest development here. At least all you can remember is the keywords. So you have, is it marker and cell method, is it volume of fluid method, is it LSM method, and by that you immediately know the level of technology implemented in the software. That's the starting point. This is really still research domain. No one really has tried it much. Okay, what is called as smooth particle hydrodynamics, which comes from physicists in a sense. Okay, and but we have not still commercial implementation of that. So by and large, when you say coupled simulation, you want to couple 4 events. You want to look at mold filling. As filling is happening, phase is changing and solidification is taking place. And as it is happening and cooling happening, you have distortion stresses coming up. And finally, your microstructure and properties. These are the 4 fundamental phenomena that you want to simulate in metal casting. Now, the issue is, if you do only one simulation, it is faster. The moment you couple 2, it becomes dramatically slows down. I mean, it can slow down by as much as 10 times. So if solidification simulation can take maybe, let's say, 1 hour, solidification plus flow for the same casting can take maybe more than 10 hours. So that's the price you have to pay for coupled simulation. So you need to use coupled simulation only when it's absolutely necessary. So governing equations in flow simulation, you have to now start putting in not only the energy balance but also momentum balance, because you have to now start calculating the velocity vectors. As velocity vectors, the velocity vector along x, y and z direction, then you get the final resultant velocity vector. So you have to compute that. Because there are 3 unknowns, you need a larger number of equations to solve. Okay? So these are the equations for governing equations for coupled simulation. What are critical inputs once again? You need a part geometry, right part geometry, you need the material properties. Now you also need additionally viscosity and surface tension, flow properties. Okay? You need a right mesh and right size of the mesh. Okay? Again, boundary conditions include one additional, these are all additional inputs, please remember that. All the inputs required for solidification are still required. These are cumulative additional inputs. So now you also need some friction coefficients or loss coefficients, because as you want to track the fluid flow. Okay? You need initial flow conditions, either filling time or flow rate or pressure. Okay? And then now you need flow models. You said metallurgical models for solidification or shrinkage. Now you need metallurgical models or flow models for Kolschat and Michelin and a few other things. And boundary conditions again, we have some more boundary conditions coming up, like wall coefficient of friction. Okay? The outlet pressure flow area, if you have flow of there in pressure die casting, those things also you need. So now you need, again, these are additional inputs from the users, remember that. And please again remember, many of these inputs, even the users cannot provide accurately. For example, mold permeability is a very critical input for gas and venting and things like that. But who knows the permeability values? The value which you get is only a sample. A real mold permeability is never constant. So you can never really predict accurately where is going to be the blowhole or gas porosity, things like that. Sometimes I feel, I go back to my old joke of all the simulation gives you accurately wrong answers. You know. Sometimes I feel do hand calculation and do some basic Excel sheets, you might get approximately right answers better than that. So we are always trying to do in IIT like good Indians, like all good Indians. We are pushing we are questioning everything. We don't accept anything on the face value. We say, okay, you say so, but tell me why it's like that. So we ask questions to all these simulation people. So our final direction of research, like frugal engineering or medical, what you're doing frugality in simulation is that we say physics, pure physics cannot answer all the questions in casting because no one really knows the equations also. On the other hand, purely experience-based things are also not good because experience is good for applying to the same set of conditions, not for a new condition. So you have these 2 problems. Simulation, no good unless your equations are right, values are right. Experience is good only for that situation, we can't use for other situation. So between what you call as experimental and simulation or physics methods, between experimental methods on one side and simulation methods on the other side, we are talking about a new kind of approach called as phenomenological methods. Phenomenological means that you do respect the experience, but try to bring the physics out of experience and put that back into equations. So equations and experience together can give you models which are semi-physics, semi-empirical, but they give you fantastically accurate results with very few inputs, with much faster computation. So our research always has been getting how to get more accurate results with less inputs and less computation. And you have seen some example of that yesterday, but we are now going to explain how some of those things work. Okay. So additional properties which you need for flow simulation are now viscosity and of course enthalpy conductivity you have seen, but viscosity is an additional input. Surface tension, if you have, is good. Now what kind of results you can expect from coupled simulation? Okay. Once you do that, now we start looking at filling time. You can look at velocity vectors in different parts of the casting as the mold is filling. Okay. And of course the traditional solidification time and temperatures and gradients you can look at that. Okay. But these 4 pictures can give you very good insight about what happens inside the mold, which you can never see through it, but you can see through the computer screen. If you couple stress also with solidification and flow, life becomes much more complex But you do need to predict things like a crack, a hot tear or a crack. You cannot simulate unless you can look at stresses and simulate them also. So these are the equations for now the coupled simulation of microstructure also. And if you look at microstructure, you can start looking at what is the phase, what phase you can expect, how much paralytic in which area, and from that you can map it onto the strength and hardness also. But remember, these are all pretty pictures. You have to finally benchmark, you have to compare with the real results and see whether they are actually working or not, and keep fine tuning all the time your inputs and your coefficients. So to summarize, we looked at when you should use flow simulation, and we said especially when you have high solidification rate. So filling and solidification both are fast, then you definitely need to use coupled simulation. That's why pressure die casting coupled simulation is absolutely necessary. Okay. Even GDC, thin wall GDC, you start need to use that. Investment casting, fortunately, although it is thin wall, I can use only solidification because the mold is hot. So my heat transfer is slow. So investment casting is not a big problem.
How to calculate the mesh size and types?
Oh, that's a good question. How do you calculate the mesh size? Okay. So you can say two extremes. I want very fast computation, have very big mesh size, one extreme end. Other end you say that I want very accurate computation, you can have very fine size. But then there is a optimal between these two. The optimal, from what we again learned from many experiments, is take the thinnest wall thickness in the part. Suppose thinnest wall thickness is 4 millimeters. Keep the mesh size at least half of that, if not 1/4 of that. So keep a mesh size for 4 millimeter wall thickness, keep a mesh size of 2 millimeters. Otherwise what will happen is if you put a 5 millimeter mesh size, the thin wall may disappear. But if you put a 0.5 millimeter wall thickness, you are unnecessarily overfilling and computation will go into days, if not hours. That's a waste of time. And in India, if power fails, and after 4 days you realize that you have set the material as grey iron instead of ductile iron, you have lost 4 days. And then your boss will say, why time waste? You go and pour the shop floor, it is faster. And I actually heard comments like that from some of the engineers who are using simulation saying, my boss is eating my head. He's saying, go out for the shop floor. We have bought the software, don't worry about it. Let it keep it in the computer, go back to shop floor. So you have to be smart about simulation. But anyway, thank you for asking that.